I've lost track of how many conceptual engineering talks I've been to where someone towards the beginning of the talk has said something like, well, we know it's possible for a group of people to change a concept or to change meaning because astronomers have done it. There was this problem with planet, and astronomers got together and they fixed everything, and now we live in harmony. And billions of people have had what it means to be a planet or what their concept of planet inalterably changed. And I think the interesting part about this story is the more we dig into it, the more it becomes clear that this sort of story, the story we tell is like so like stripped down and simplified that it's almost fiction. And so I'm hoping today to sort of challenge the story we've all been telling each other that, oh, in fact, we can engineer, we know it's possible to do conceptual engineers because astronomers have done it. Because when we look at the details, not only is the story a lot messier, but it's not clear that that's what they actually did. So I'm more than delighted to bring together a panel of people. We're going to have two parts of this. So we're going to start with a talk by Celine Henne and Janna Müller. Celine is a postdoc at the University of Toronto, where she is working on something very close to my heart, the intersection of American pragmatism and conceptual engineering, with a specialty on John Dewey, and has published on topics in conceptual engineering and where else, synthesis and inquiry. Janna is a PhD working in the History and Philosophy of Science department at the University of Cambridge, and Janna's work is on the concept of asteroid during the 19th century. And as we will see during their talk, the history of the concept of asteroid and the history of concept of planet are sort of deeply intertwined during that time period. So they're going to start and give us like sort of a bit of a background to highlight the fact that the history of the concept of planet is actually very messy. And it was particularly messy during this period in the 19th century. And then we're going to move on to the second part, where we're going to talk with Mike Brown. Mike Brown is the professor of planetary astronomy at Caltech. He is perhaps best known by the title of his autobiography, How I Killed Pluto and Why It Had It Coming. So Mike Brown led the team that discovered Ares, then Xena, sort of the first trans-Neptunian object other than Pluto, or like the first large trans-Neptunian object. I'm getting my astronomy concepts mixed up, beyond Pluto, and was in fact led a team that discovered a whole bunch of these things. The large trans-Neptunian objects aren't exactly household names. The ones you might have heard of are very much are his team's discovery, including Sedna, Makemake, and Quaher. So he will be talking about sort of what happened in those fateful 2 weeks in 2006 and some of the background and foreground of that. So now that we've done all these introductions, I'd like to hand it over to Celine and Janna.
Great. Thank you so much, Ethan, for putting together this panel, and thanks for everyone who's here. So what we want to do in this paper is to provide a perspective from the history and philosophy of science to illuminate certain aspects of conceptual engineering. So as Ethan said, this new definition of planet issued in 2006 by the International Astronomical Union is very often used as an example of successful conceptual engineering in science. But what we want to do here is to go further back in time to show that this definition or this new development is actually only the latest and probably not the last iteration in a very long history of the concept.
So we will be looking at a crucial moment in the development of the concept of planet in the early 19th century. Between 1801 and 1807, 4 new objects were discovered in the sky, which we now call asteroids and minor planets. We also know that there are 4 slightly larger pieces of rock out of about 1 million smaller ones that had been discovered in the last 200 years. So in the early 19th century, however, these discoveries were a sensation. It was believed that the 8th, 9th, 10th, and 11th planet of the solar system had been discovered. So Sirius, Pallas, Juno, and Vesta were not only given names of Roman deities, but also, like other planets, their own symbols. According to dominant historical scholarship, that remained true until at least the mid-19th century. So a closer look at that narrative will show a more complicated picture. While most astronomers in the early 19th century were inclined to classify these new objects as planets, not everyone shared that view, actually. Even among those who did, there was a substantial debate concerning the definition of a planet and the suitability of these celestial bodies for that category. So one notable dissenter was William Herschel, the discoverer of Uranus. In 1802, he published an essay in the Philosophical Transaction of the Royal Society in which he articulated definitions for both planets and comets. And then this framework led him to propose that the newly discovered celestial objects constituted a distinct class, which he termed asteroids due to their star-like appearance. This initiated a debate on the nature of these celestial bodies.
Right. So the philosophical lens that we've chosen to analyze this debate is that of Friedrich Waismann's notion of open texture concept. So open texture refers to the partially indeterminate character of most of our empirical concepts. According to Waismann, concepts are not delimited in all possible directions. So for this, for him, it means that it's always possible for a concept to encounter an unexpected case that lies beyond its standard range of application. So when that happens, its application becomes indeterminate. It's not clear whether or not the new object encountered falls within or outside the extension of the concept. And H.A. Hart developed this idea in the context of law, and he said that concepts have a core of certainty and a penumbra of doubt. So the main idea that we want to pursue here is that the confrontation of open texture concepts with the object that lie in their fringe or in their penumbra is something that requires conceptual engineering, a type of conceptual engineering that seeks to resolve the indeterminacy. And so the idea here is to interpret the concept of planet as one such open texture concept, which in the early 19th century, like we will see, was confronted with 4 objects that lie just outside of its standard range of application. And this confrontation triggered debates regarding the way planets should be understood going forward. So we will focus on 2 aspects of the debate that are relevant for conceptual engineering. First, on the origins of the debate. So these new empirical discoveries that led to the articulation and reevaluation of the concept of planets. I think that most conceptual engineers do not often say much about how the question of evaluation and revision of concepts even arises. So here we think it's important to stress the context in which that question arose. And second, we'll focus on the reasons, both implicit and explicit, that supported each proposal. So what we will see is that there were 2 distinct proposals, 2 definitions that arose in this context, 2 definitions of planets. And here we understand reasons both in an explanatory sense, so what contingent factors can explain the preference for one proposal over another, and in a normative sense, so what justificatory grounds were put forward for each proposal, each definition. And the structure of the talk will be in 4 parts, so with following roughly this structure with an alternation between history and philosophy.
So to start, we'll have a brief look at the historical context in which the debate arose. So although no official, widely communicated definition of planets existed, there was a tacit or historically rooted understanding of how planets could be identified through observation. This understanding had evolved over centuries. So in antiquity, while planets were perceived as wandering stars called planetes in Greek or stellae errantes in Latin, objects that had moved against a background of fixed stars, basically. The prevalent geocentric model included 7 planets, including the Sun and Earth, Moon, as moving objects in the sky. Then the discovery of 4 moons of Jupiter by Galileo increased this number to 11. The Copernican heliocentric model, established during the course of the 16th and 17th century, reshaped the understanding of planets in a way that the Sun was no longer considered a wandering planet, but Earth was classified as one. In the 18th century, with the discovery of more extraterrestrial moons, planet satellites were no longer considered to be primary planets. With the discovery of Uranus in 1781, the solar system then had 7 planets moving in Keplerian orbits around their central star. So the idea of additional planets within the solar system had intrigued astronomers in the preceding centuries. Kepler and others had suggested that the existence of an undiscovered planet in the gap between Mars and Jupiter, which seemed rather big, with Johann Daniel Titius quantifying this gap using an arithmetic pattern later known as the Titius border law, or TBL. When William Herschel discovered Uranus with a distance from the sun conforming to this pattern, it solidified the credibility of this concept planet in the 18th century. So the planet in the 18th century, just before the discoveries of the asteroids, then became a celestial body that moved in orbits around the sun in the places described by this TBL. One astronomer who was convinced of the correctness of this rule and thus the existence of another planet between Mars and Jupiter was Franz Xaver von Zach, court astronomer in Gotha in Germany. In his search for planets, he founded the Vereinigte Astronomische Gesellschaft in 1800, also called the Celestial Police, together with 5 other German astronomers. Their correspondence represents an interesting source for the discussion about planets and asteroids in the early 19th century and can be seen here in a quite simplified way as a counterpart to Herschel's proposal of a new category of celestial bodies. So it is in this context that Sirius, Pallas, Juno, and Vesta were discovered in between 1801 and 1807. So all these 4 new bodies were discovered when astronomers compared star maps to the actual sky, identifying moving objects over several observations. When Sirius was discovered, astronomers had difficulties determining its orbit, as both near-circular like the other planets or parabolic orbits like comets did not seem to fit. In the end of 1801, mathematician Carl Friedrich Gauss developed a new method to accurately determine Sirius orbital parameters, including a slightly higher eccentricity and inclination to the plane of the other planets. So in general, it was quickly seen that the new objects had a few peculiar properties, which seemed not quite planet-like. First of all, suddenly 4 objects appeared in the space which astronomers had initially anticipated to find 1 between Mars and Jupiter. This already generated some degree of uncertainty regarding the nature of these celestial bodies. Their appearance was also peculiar because Sirius and Pallas, according to, for example, Herschel's observation, lacked a distinctive planetary disk you can see in the other planets, and their kind of hazy appearance in the telescope reminded them of that of comets, although they were significantly smaller, or even the blurry appearance of fixed stars when you observe them through a telescope. Furthermore, their orbits were more eccentric than those of the known planets. While the planets of the solar system, except for Mars and Mercury, have eccentricities below 0.06, the new bodies displayed slightly higher values, as you can see here. And the inclinations were also noteworthy in a way that they were greater than the other planets. So Gauss calculated Vesta's inclination to be approximately 8 degrees in 1811, while Sirius and Juno had slightly greater inclinations, and Pallas displayed an inclination of almost 35 degrees to the plane of Earth orbit. And also their diameter was smaller as well. So Herschel attempted the first measurements of diameters of Sirius and Pallas, and he showed a huge difference, as you can see here, to other planets. Although we now know that they are a little bit bigger than Herschel actually measured during that time.
Right, so just a few words maybe on the notion of concept that we're using. It's pretty loose, but I'm happy to clarify maybe in the Q&A. So on the view that we're using, concepts are human creations that are formed in certain contexts for certain purposes. So in a very simplified way, we can say that the concept of planet was formed to classify celestial bodies observed by the naked eye and later by telescopes in a way that facilitates inference and prediction. And to identify concepts, we identify them in terms of the implicit and explicit rules of use for the linguistic term planet here. So we suggest looking at the concept of planet as an open texture concept. This means that in some periods, the concept is unproblematically applied to the objects that are in its standard range of application. So all of the objects to which the concept of planet applies can be all intuitively and determinately classified either as planets or non-planets. So they're either planets or something else, like a star or a comet. And there was such a period of conceptual stability in the 18th century, which includes the discovery of Uranus. There was no debate about whether Uranus is a planet or not when it was discovered. So just to clarify maybe what I mean by this idea of a standard range of application. So I take this expression and this idea from Mark Wilson, and it can be understood as the implicit parameters and conditions in which a concept is usually applied and in which it works effectively at a certain time t. So the standard range of application of the concept planet in the 19th century included objects that are similar enough to the ones already classified as planets, stars, and comets by astronomers. So what we see with the discovery of Ceres, Pallas, Juno, and Vesta is the confrontation of this relatively stable concepts with objects that do not fit the existing classification, do not quite fit the existing classification. So I think Hart's idea of a penumbra is quite useful here because they are neither totally in the light, so then they're not straightforwardly in, nor totally in the dark, straightforwardly out. But they are both similar enough to planets that they could fall in its extension, but also dissimilar enough that the question of their inclusion cannot be straightforwardly settled. So what we see next is quite interesting. It's the confrontation of this planet to unexpected objects, which leads astronomers to make explicit the largely implicit rules of use that guided their application of the term planet. And the really interesting thing is to see the emerging disagreement between two camps, so Herschel on the one hand, and the German astronomers or celestial police on the other hand, which highlight two different directions in which the partially indeterminate concept could have taken.
Yeah, so let us have a closer look at the actual debate and start with Herschel. So he was astonished by the new body's quote-unquote very particular nature, which appears to be rather cometary than planetary. Herschel asked a very interesting question, namely, what are these new stars? Are they planets or are they comets? And stars to be understood as generally celestial bodies. So as a basis for answering that question, he first drew up a list of properties we have, quote-unquote, hitherto affixed to the term planet, giving an explicit definition of this kind of celestial object. So for him, planets are celestial bodies of a certain very considerable size. They move in not very eccentric ellipses around the sun. The plane of their orbits do not deviate many degrees from the planes of the Earth orbit. Their motion is direct, meaning that they all move in the same direction. They may have satellites or rings, and they have an atmosphere of a considerable extent, which however bears hardly any sensible proportion to their diameter. This is in contrast to comets, whose atmospheres, or more accurately comas, make up a significant proportion of the total diameter. And their orbits are at certain considerable distances from each other, which refers to the Titius-Bode law. So according to these measurements, Ceres and Pallas were significantly smaller than the known planets. So Herschel said, we can certainly not class them in the list of planets. The inclinations were also more than twice as great of those of the other planets, which also led to an extension of the zodiac, so the region of the sky where all the other planets move in, if they were to be classified as planets. Their atmospheres or blurry appearances also reminded him more of comets' comas, meaning much larger than planets, even though he also found that cometary comas were considerably larger. Finally, Ceres and Pallas also contradicted TBL because their orbits were too close together to match the general harmony of the other planetary orbits. He has thus found a clear contradiction in the first, third, sixth, and seventh criteria with regard to Ceres and Pallas, and then after comparing them to comets, he determined what was specific to him about the new celestial bodies. So he said, as planets are distinguished from the fixed stars by their visible change of situation in the zodiac, and comets by the remarkable comas, so the quality in which these objects differ considerably from the former two species is that they resemble small stars so much as hardly to be distinguished from them. And further, from this, their asteroidical appearance, he would call them asteroids. These bodies will hold a middle rank between the two species that are known before, so that planets, asteroids, and comets will in future comprehend all the primary celestial body that will either remain with or occasionally visit our solar system. The observations of Ceres and Pallas in 1801 and 1802 puzzled German astronomers as well, which also caused a discussion whether these new bodies were actually planets or not, and made an explanation of what determined the nature of planets necessary. Discovered as luminous points that had moved against a background of fixed stars, the most pressing issue at first was to determine the motion of Sirius and Pallas in order to find them again and to enable other astronomers to observe them at all. So the result of this discussion among the German astronomers was that Sirius and Pallas are planets. They called them planets and they explicitly rejected Herschel's term asteroids. To say that, they had to construct a planet definition, however, that included the new objects, a process that went on hand in hand with more and new observations. So let me summarize quickly how the German astronomers addressed the peculiar properties of Sirius and Pallas in their relation to planethood. The presence of two celestial bodies at that time in the region where a planet was traditionally expected, as defined by the TBL, was surprising to them as well. So some, like Zach, questioned the TBL and only considered it an empirical inference rather than a necessary criterion for planethood, suggesting that it should be abandoned. The German astronomers found Herschel's measurements of the diameters of these objects to be unbelievably small. So Johann Schröter, another member of the Celestial Police, also measured Sirius and Pallas, revealing larger diameters closer to those of Mercury or Mars, between 4,000 to 5,000 kilometers. This led to an argument that a wide range of diameters existed in the solar system, from the small ones like Mars, Mercury, or the new ones, to the big ones like Jupiter, challenging the notion that planets had to be of a certain size. The Germans also noted that a hazy or blurry appearance in this new celestial body was existent, but unlike comets, they lacked extensive tails, as you can see here in this drawing from that time, making them easily distinguishable. So as in centuries before, that was basically the only regard in which appearance played a role in distinguishing celestial objects. Sirius and Pallas had great inclinations, causing them to move outside of the zodiac. However, the German astronomers treated the idea of the zodiac as a criterion for planets similar to the TBL, as an empirical concept that could be extended as needed. Hence, the inclination of orbits was considered irrelevant for defining planethood as well. And last but not least, Sirius and Pallas moved in elliptical orbits, meaning with an eccentricity smaller than 1, consistent with Kepler's first law, just like the classical planets. While their eccentricities may have been slightly larger than those of the traditional planets, they were not deemed significantly different, especially when compared to the hyperbolic or parabolic orbit of comets. Eventually, they came to the conclusion that planets are to be classified according to the elliptical heliocentric motion in the spirit of Kepler's law and in accordance with the historically known sense of planets as wandering stars. In contrast to Herschel's rather narrow planetary definition, which excluded the new celestial bodies, an apparently simple and much broader planetary definition was negotiated here that included new objects. So planets were celestial bodies that moved in elliptical orbits around the sun, and Sirius and Pallas fit that conceptualization. So when Juno and Vesta were discovered in 1804 and 1807, the German astronomers had already dismissed size, the TBL, and inclinations as relevant criteria for planethood. The new bodies were then easily accepted as planets by simply mentioning their moderate, or in German, mäßige eccentricities. As Zach summarized in 1811, I think most continental astronomers agree that it's not the magnitude of volume, distance, inclination, and eccentricity that constitutes the essence of a major planet, but this consists mainly in the elliptical or circular orbit around the sun. Nevertheless, the German astronomers did acknowledge that the four new objects had certain properties in common that they did not share with the classical planets and Uranus, which made them peculiar, but in their opinion, not planets. So in the following years, the term small or simply new planets became established in their correspondence when referring to the asteroids. With their wide and really inclusive concept of planets, the German astronomers, and following them most other European astronomers, simply did not see a need for a new and third category of a celestial body, leaving Herschel pretty much isolated with his proposal. So the debate was settled, at least for the time being. Just to give you a quick idea on how this continued in the later 19th century. So in 1845, almost 40 years later, another object similar to Sirius and the others was discovered in between Mars and Jupiter and was therefore considered to be a planet. So when Neptune was discovered 2 years later in 1847, it was then counted as the 13th planet of the solar system. By the end of the century, however, the number of objects between Mars and Jupiter rose to over 400, which caused a renewed debate on the classification of those celestial bodies, and then they were eventually stripped of their planetary status. And I think we will hear pretty soon that a very similar new debate followed the discovery of Kuiper-Belt objects in the 1990s, culminating with a definition of planets and dwarf planets in 2006.
Right, so going back to the structure of the debate between Herschel and the German astronomers, here it's quite clear that we have a conceptual disagreement rather than a merely factual one, as evidenced by the fact that empirical facts regarding the diameter, inclination, orbit of the objects could not settle the question of the inclusion or exclusion of these objects in the extension of planet. So they did play a role in the arguments that were put forward by each party, but each of these characteristics can just be dismissed as irrelevant by each party. So the debate, I think, that followed between Herschel and the German astronomers can be understood as a kind of conceptual engineering in which the goal is to resolve a state of conceptual indeterminacy. So to put it in Wittgensteinian terms, there are different ways in which astronomers could go on to use and apply the term of planets, and a choice needed to be made. I think this debate has a particularly interesting feature, which was also noted by Mark Wilson with respect to the own examples that he used in his article, his own examples of open texture concepts. The interesting feature is that neither Herschel nor the group of German astronomers believed that they were changing the concept of planet. They both believed that their use was perfectly continuous with previous use, and that they were correctly applying the very same concept that they were using, for example, when classifying Uranus as a planet. And indeed, we can see that both definitions that are put forward are perfectly consistent with the previous use, and they fit with the characteristics of the standard or stereotypical example of planets. So Mars, Jupiter, etc. So here's a visualization of what happens. So the two definitions are coextensive to the period of time when the concept was used within its standard range of applications. So when it was only confronted with standard or stereotypical planets that are similar enough to the ones that were first classified as planets. But once this range of application is extended to objects, to include objects like cirrus, Pallas, etc., so once this concept was confronted with these new objects, they then come apart. And what makes it a genuinely open texture concept is that there was, I think, no way of predicting, just if we stay at time t0, just from observing the previous use of the concept and the characteristics of the objects that were part of its standard extension, in which direction the concept could have gone or even should have gone. So now looking more at the functions that the definitions played in this debate, a temptation is just to say that astronomers had been using two distinct concepts of planet all along, but only realized it when they encountered these new objects. So a temptation is to say that the definition simply revealed the presence and equivocation of two concepts of planet. But I think this retrospective reconstruction is quite unrealistic. So I propose to interpret the definitions as having two functions. So one is indeed descriptive. So they do make explicit some of the implicit rules that guided their application of the concept of planet. But they also rationalize a posteriori, so or retrospectively, they rationalize their mostly intuitive decision to classify Sirius, Pallas, etc., as planets or non-planets. So Herschel will construct a definition of planet in a way that excludes Sirius, Pallas, Juno, and Vesta, while the German astronomers construct a definition of planet in a way that includes Sirius, Pallas, Juno, and Vesta. Now, the question is, since two definitions that both fit the standard example of planets and fit with previous use have emerged, how do we choose between these two? What are the reasons, both explanatory and normative, that support each proposal? So I think that there are normative reasons, for example, in terms of the theoretical and epistemic virtues that support each proposal, although they may not have been sufficient to decide in favor of one or the other. So both need to be empirically adequate, so they need to fit with the observed characteristics of planets. I think there are also desiderata of simplicity, inferential fruitfulness, and unifying scopes. So it is better if a few characteristics can explain or correlate with the presence of other characteristics. That's what makes it a useful concept, right? We only need to observe the presence of FGH in order to be able to infer the presence of other characteristics, i.e. K. But we also don't want to multiply categories unnecessarily, right? We don't want to have too many categories in our classification of celestial bodies. But I think there are also explanatory reasons that explain so historically contingent causes for the choice of each definition, in terms of first the kind of interest that guided each of the astronomers' research, what kinds of instruments they were using, what kind of methods they were using to find and study the objects. So here I'm presenting findings from Janna's research, which shows that these contingent factors played actually a very important role in making some characteristics of planet relevant or irrelevant for each team, and so played a very important role in the decision of Herschel or the German astronomers to either include these bodies as planets or exclude them as planets. So Herschel's research practice focused on the appearance of celestial bodies using his high-resolution telescopes. He was interested in defining a characteristic of celestial objects that would enable him to determine their nature by only making a few observations, as opposed to tracking them over a long period of time and using time-consuming calculations. So informed by his interest in the appearance of celestial objects, including stars and nebulae as well, and with the help of his excellent telescopes, his thinking led him to conceptualize a third kind of celestial objects in the solar system, which were characterized literally as what he saw in the telescopes, star-like shapes. The German astronomers, on the other hand, were searching for a missing planet at the time of the discovery. So the group consisted mostly of people that were concerned with collecting positional data and calculating orbits in their professional everyday life. So their focus was, in contrast with Herschel's, on the motion of Sirius, Pallas, Juno, and Vesta. And although they did take Herschel's observations and the characteristics that he emphasized seriously and discussed them, they played only a secondary role in their discussion about what constituted planets. So what we see here is that both of these definitions were articulated and defended largely on the basis of intuitive decisions to classify these bodies as planets or not, which were themselves guided mostly by very contingent interests. So by way of concluding remarks, I want to now tie it back together to conceptual engineering, considerations regarding conceptual engineering. So here the question may arise whether it is indeed a case of conceptual engineering. So we've said a little about how the debate was settled, and then it was reopened later in a later 19th century. But I do think it is worth considering this debate as some kind of conceptual engineering. So it's not merely disambiguating and choosing between two uses of definitions of the term planet. I think there's a constructive element to this debate, which includes a formulation and articulation of definitions, and then a choice between better or worse definition. There's an evaluative element, right? We want to evaluate which definition fares better, maybe with respect to certain purposes. There's a transformative element. This choice will then determine future practice. And there's a normative element. This choice prescribes the correct use of the term. Versus maybe a merely revelatory or merely descriptive enterprise with respect to the concepts that we do have. So I think this qualifies as a kind of conceptual engineering. And what we have presented, of course, is a very specific kind of conceptual engineering, right? One that arises from this open texture characteristics of concepts. But I think we can draw some general lessons for conceptual engineering. So first, I think the interesting thing to know is that we rarely have a clear-cut two-step process, right, in which the concept is defined and then it is applied to objects. Instead, the two processes go hand in hand, as we've seen. It is in the course of applying concepts that we come to reflect on them and revise them. And I think this should be accounted for in the theory and practice of conceptual engineering. We're working from and with examples constantly. And at least with respect to sortal concepts like planet, the reasons for and against a certain proposal or definition are inseparable from the reasons for and against including or excluding certain objects from its extension. They go together. And I think such occurrences are crucial moments for the analysis of the concept, its evaluation, and its revisions, right? Occurrences in which we confront a concept with weird cases or unexpected cases. And I think that thought experiments can be used to fabricate such occurrences, right? Sometimes it's empirical, so in this case, we have no choice, but being faced with new empirical discoveries that make us reflect on the concept, but we can also fabricate these occurrences. So taking a concept outside of its standard range of application in weird scenarios. So that's already done in conceptual analysis, but I think it can also be used in conceptual engineering. But of course, we should be beware of the contingency of factors that guide our conceptual intuitions and conceptual choices in these cases. So it doesn't mean we should dismiss them. That doesn't mean they're either intrinsically good or bad, but we should make them explicit, maybe the contingent interests that guide our intuitions, and we should then make them part of the evaluations. So to assess them as are they actually epistemically or practically relevant or irrelevant. That's it. Thank you.
All right. So, Mike, I guess I should introduce you again. You have the dubious distinction of being the only person. There was about 18 months where you're the only person since 1930 to have discovered a planet. And now you will forever be the person who discovered -1 planets, which I think is a...
Not necessarily. If I discover one more, I'm back to 0.
You're back to 0. I like that optimism. So as a way to sort of bridge the gap, can you sort of bring us back to like the late 90s, early 2000s, and think where was astronomy in terms of like the Kuiper Belt and Pluto? How was the community thinking about that around then?
Yeah, so let me start in 1990, where there was no understanding that there was a Kuiper Belt out there at all. So in 1990, Pluto was a well and good planet, even though it was weird. It was known finally how small it really was. It's important to remember that when it was discovered, people thought it was huge. The New York Times headline says it's the size of Jupiter, which is only wrong by a factor of 250,000. But in 1990, it was known to be small, and it had this weird orbit. You know, it's all about the orbits again, just like we were hearing about the asteroids. It's got an eccentric orbit. All the planets have circular orbits, circular-ish orbits. It's got an orbit that's tilted by about 20 degrees. All the planets are in the plane of the planets. But there was nothing else to call it. So it was still considered a planet. People were talking about sending a mission out there, and everything was good. In 1992, the first new object was found out beyond the orbit of Neptune by a pair of astronomers at University of Hawaii. And when that one was found, people were like, yeah, maybe it's just a one-off thing and there's nothing else going to be found out there. But very shortly after, the second one was found, and then the third one was found. And as of today, there are, I lose track, there are probably 4,000 known objects out there in the outer solar system beyond Neptune and what we now call the Kuiper Belt. For the astronomers who were paying attention, I had just actually gotten my PhD like right then and was kind of looking for what I wanted to work on. I'm like, wow, this is the coolest place in the solar system to go work on, actually, literally. And so I started working on these objects, and it was really clear that this population is where Pluto belonged. These objects out beyond Neptune also have eccentric orbits and tilted orbits, and they're small like Pluto is. So it all kind of made sense. So for those astronomers, it was very clear that Pluto rightly deserved to be called a Kuiper Belt object, but there was not actually that much impetus to then take away its planetary status because, it had been a planet for long enough that it was going to be a fight that nobody really wanted to fight. So that all came about really when we started doing big wide field surveys and started finding these objects that became the scale of Pluto itself. The first objects were all small, a couple of 100 kilometers. Pluto is about 2,400 kilometers across. And so when those small ones were there, you could say, yeah, but Pluto is still bigger than all the rest of them. And then we found one that was about half the size of Pluto. And then we found one that was about 2/3 the size of Pluto. And finally, we found one that is basically the size of Pluto. And you knew at that point that something had to give. Either this new thing we found that's now called Eris. Originally, we named it Xena after the warrior princess. You knew something was going to have to happen. Either there was going to have to be a new planet added, or there was going to have to be planets subtracted, or many new planets added, or something. So as soon as Eris was discovered, we knew things were going to change. We just didn't quite know what astronomers were going to do at that time.
Yeah, so this is something I'm not quite clear on, is sort of during that period in like 2006, 2007, as you've discovered these, was the thinking that like there were like 1,000 of these objects in the Kuiper Belt, or that there were like 3, or you just didn't know? Of
the scale of sort of Pluto scale
Yeah.
objects? Is that so we didn't know the real answer, but we knew there weren't 1,000 because we had done a pretty good survey of the whole sky for things of that size, and we had only found Eris. So there might be a few more, and we still actually, since that time, we haven't found anything else that's more massive. So Eris, it turns out, is about this much smaller than Pluto, which irritates me to no end. But it's actually about 25% more massive than Pluto. So we'll talk about the massive one. So it's the most massive object out there. We have not found anything else yet any more massive than Pluto. So it was the only one known. And if there were only things a little smaller than Pluto, you could still get away with sweeping it under the rug. And I do believe that astronomers would have probably continued to sweep it under the rug and just say, yeah, well, Pluto, it's grandfathered in, it's something else. But once you find something that clearly has to be it has to be the same as Pluto, one way or the other. So either it goes in or Pluto goes out.
Yeah,
it's an interesting, because I say it has to be the same as Pluto. There were those who would have said, no, it doesn't. Pluto's a planet because we said so. This one, though it's more massive, no.
Yeah, I guess the next question I wanted to ask you is what the conversations were happening, like both publicly and behind closed doors, in that space. Like, was that January 2005 to August 2006? I think that's the right. Like, what sort of
right.
What sort of conversations were being had, sort of publicly and privately about this?
So a lot of them. So the most private of the ones were between me and my wife, and I said, oh, look, we just found something that's bigger. At first we thought it was a little bit bigger than Pluto. We didn't. Actually, we had the size right. They had the size of Pluto wrong. Pluto actually grew a little just to make it a little bit larger than Eris, which is, again, very irritating. But so we knew we found this thing that was a little bit bigger than Pluto, and I explained to my wife, I was like, okay, we're going to do a press release about this discovery, and I'm going to say in this that it's not a planet, because I have a very clear concept what I think a planet is. Now I know what I am. I'm a Herschelian. I did not realize until today that I really am just channeling Herschel. Herschel's definitions, I would take away a few of them, but that's basically how I feel about what a planet is and is not. And so I explained to my wife that I'm going to say it's not a planet. She's like, are you really? And I was like, of course I am. It's not a planet. She's like, yeah. She said, irrelevantly, think of your daughter, who was 3 weeks old at the time. She could be the daughter of a planet discoverer. I'm like, really? Is this relevant? And in the end, it's actually here's how these things go. The press officer at Caltech convinced me in the press release we should say it was a 10th planet. And I went along with it because I figured it's win-win. I don't believe it's a planet. When people argue and say it's not a planet, I can then, say, okay, you're right. Or in the end, I wasn't convinced Pluto would ever be demoted, so it was going to be a planet anyway. So that was the private conversation going on. But in the conversations amongst astronomers who mostly studied these objects in the Kuiper Belt, all of us had understood long ago. I think all of us are generally, on the Herschel camp, and they're like, these things are not planets. Even if you find one slightly bigger than Pluto, it's not a planet, and we knew that. But there was a subset who really adamantly wanted to keep Pluto as a planet. And actually, I'm fascinated by this, the back and forth between Herschel and the Celestial Police, because there's a very analogous situation, and in something that that was not mentioned. Of course, Herschel did not want these things to be planets. Also, Herschel discovered the most recent planet, and if suddenly all these other things are planets, Herschel is no longer as special as he used to be. The Celestial Police discovered all these things, and they get to be planet discoverers if they're planets, or they don't get to be. So I mean, I think that there is a lot of self-interest in that, contingency of factors. Self-interest is one of them, and I think this came into play in the Pluto debates too. The people who were most adamant about Pluto staying a planet were the people involved in the NASA mission that was already on its way to Pluto. And when they built it, when they launched it, it was going to a planet, and they felt very put out that suddenly they were going to something that wasn't a planet anymore. And so their definition, the debates were often ways of keeping Pluto a planet. It was not like, let's all sit in a box and think about what a planet should be. It was, let's all decide Pluto's a planet and now make up a definition that fits Pluto as a planet. That's really how those two, I mean, in the end, it was the same two debates. It was the same Herschel and Celestial Police. It was people who thought that big important things were planets and people who thought everything should be a planet. Same debate, but it was also in many ways the same, at least on their side. Our side, we are not self-interested. Only everybody else is self-interested.
All right, so let's get to like the big climax then, and then we can sort of talk about the aftermath. So there's a big thing. I feel weird explaining this to you since you're the expert here, but we have to get it on the table. In 2000, there's a big every 3 years, there's a big astronomy conference, the International Astronomy Union, lasts about 2 weeks. And at the end of the one in 2006, in a vote, they said, here's what makes it a planet. Here are the 3 conditions for planethood. Do you want to? I can do it. You can do it.
Let me do it so I can do it disparagingly, because it's best to do it disparagingly. So let me set the stage. So the first, there was an initial proposal at this IAU meeting, and the initial proposal with a committee had met and talked and debated. This was about the 4th committee but this one finally came to a decision, and the proposal was everything that goes around the sun and is round is a planet. And they said specifically that means, all the 9 ones that we know about, plus add Eris, which is the one that was more massive than Pluto, 2 of the other ones that I'd found, Maki and Haumea, which is not round, which is awkward, but there's a reason for that. And in the dumbest political move you could possibly make, they said, also, by the way, we're going to add Pluto's moon Charon as an independent planet, for the reason that Pluto and Charon Charon is big enough compared to Pluto that when they go around each other, they actually go around a common center of mass that's outside of Pluto. And so the argument is that Charon is actually going around the sun, not around Pluto, which I have to say is one of the dumbest things I've ever heard anyone propose, because it's just like, okay, like, we're trying to decide whether to count Pluto as a planet, and they're like, yes, and its moon is too, just doubling down on forcing Pluto to be a planet. And I really believe that was one of the things that finally led people to just get fed up with this whole committee's recommendation and say, this is ridiculous. And so the astronomers present basically tossed out the committee's recommendation and came up with one that we have voted on today. There are 3 criteria, and I think that it's important to note that in the field of astronomy, there is no other lawyer-like definition like this of any object in the sky. Stars don't have a definition, galaxies don't have a definition, nebulae don't have a definition, but planets have a very lawyer-like definition. They have to go around the sun, they have to be round, and they have to have cleared their orbit. And if you go back to Herschel's definition, that very first definition of Herschel was they had to be of a substantial size. I think that was the phrasing of it. that clearing the orbit always gets people a little confused, but it really just means it has to be of a substantial size. It has to be the big enough thing in it. Actually, and Herschel had another one somewhere down there that it kind of had to be the only thing in its orbit. Do I remember that right? Is that what one of those was like? There can't be multiple things all in the same orbit, and that kind of what's that clear the orbit is thing too. So it really is basically Herschel minus the weird atmosphere stuff that Herschel was worried about, and there are no restrictions on eccentricity or inclination as long as it clears its orbit. So that's the definition. But in astronomy, once you have lawyer-like definitions, you get lawyers involved, and almost literally. There is actually one astronomer who also has a law degree and started arguing about this all the time. He's like, well, there are near-Earth asteroids that cross the orbit of the Earth, so clearly the Earth is not a planet, which of course the Earth is a planet. And there are asteroids in the orbit of Jupiter, so clearly Jupiter is not a planet. Again, of course, Jupiter is a planet. But what that shows you is that it's not. The definition is not really a very useful thing. I think it's really an attempt to describe the concept, and the concept is really, again, it's Herschel again. It's that these large, important bodies in the solar system are the things that we call planets. And in our own solar system, we see that they're on these very majestic circular orbits in a single disk around the sun. And then there are small bodies that flit in and out of all these things, and we don't call them planets. It's a very clear concept. It's a difficult concept to really precisely write a definition of. Actually, one very smart astronomer, and I forget who it was, tried to get the IAU to put in a footnote in the definition that said, in our solar system, this is the 8 planets, a list of, and they're like, well, we don't need that. And I'm like, actually, that's exactly what you just did. That's the right definition. In our solar system today, we call these things planets for a lot of different reasons that we have to sort of figure out. It's interesting, though, I will point out, like around other stars, some of these things don't work as well. We talk about the nice circular orbits, the nice things all being in one plane. Doesn't work that way around other stars in our galaxies, and it might not even work that way in the very outer part of our solar system. If we ever find this real ninth planet that we're looking for out there, it would be on a very eccentric orbit. So some of those things that we think of as planetary characteristics don't even fit. But it really is the big important planets, the big important bodies in our solar system are the things that we call planets.
Yeah, I guess like just to circle back and kind of sort of push you on something you said. So like the actual like official like stamped in rubber like sealed proclamation has like the 3 definitions, and then also it has the footnote. You know,
it does not have the footnote.
It does not have the footnote.
No,
they didn't.
They didn't accept that amendment, and I'm sad they didn't.
Yeah. So I read somewhere that like, so the actual wording is that like Mercury is in hydrostatic, like it's hydrostatic equilibrium. It's not round, like, but Mercury's not in hydrostatic equilibrium, or so I've read.
It is. It's close enough. Again, it's a definition, right? So if I have a definition, I mean, the Earth is not in precise hydrostatic definition equilibrium. So then you have to be, it's in equilibrium enough, I would say. And so the concept is good. The definition, if you're going to write a definition, I think you want to have clear definitions and decide from your definition. But I think having a definition is a bad idea to begin with. And I would just throw it out the door. And we all know what we're talking about when we say the big important things. And so again, one of the objections is, well, what if we go to another planetary system around another star and we find something like 2 big objects going around each other the size of Jupiter? We need a definition to what we're going to call them. And my response to that is, are you kidding me? You go find 2 things like Jupiter orbiting each other, and your big concern is, what do we define it like? Like first off, jump up and down and be excited about the science. We'll worry about the definition later. We can expand and contract things, but we do not need to make all the boxes ahead of time to put in all the phenomena that we haven't discovered yet in the universe.
All right, so I have 2 more questions, and then we'll open it up. Just so to give you another opportunity to rag on the committee, what's the dwarf planet?
Oh, that's the worst. Okay, so dwarf planet is the definition was if you fit 2 but not the 3rd criterion, then you're a dwarf planet. So if you go around the sun and you are in hydrostatic equilibrium, how much? Unclear. But you don't clear your orbit. You are a dwarf planet. And the dwarf planet is a awkward term because, of course, it has the word planet in there, and people then argue, of course, if it says planet, then it has to be a planet. And I point out that seahorses would like to have a conversation with you at this point. But the only reason that the phrase dwarf planet came to be is because the people who were trying to keep Pluto a planet inserted the phrase dwarf planet in there and inserted a forced third vote in that IAU meeting to have it explicitly say that dwarf planets are planets. So they could say, okay, sure, Pluto's a dwarf planet, but it's a planet, and it was voted down very soundly. But that's why that awkward phrase is in there. We actually have used that phrase, a similar word to describe those same objects for a long time before the IAU, and it was basically going off of Herschel. Herschel named these things asteroids. We called the small round objects that were not planets, we called them planetoids. And I actually wish that we had retained that instead of the more awkward dwarf planet one.
All right, final question, and then we'll open it up. And I think this fits well into the first talk, which is, if you were king astronomer,
I am.
Yeah, close enough. How would you split up the solar system into types of things?
Oh, it's easy, and it's fascinating, and it's important. Like if you sit down on an airplane next to some astronomer and you say, which is, if you sit down next to an astronomer, the first thing you're going to ask, I know this because this happens all the time, is like, what was that thing about Pluto? And most astronomers will tell you, it doesn't matter. It's semantics. Pluto doesn't care what you call it. And sure, the word might be semantics, but I actually think that what it is for a scientist, it's classification. And classification is critically important in science. Classification is how we begin to understand phenomena in science. And so in our solar system, the classification, it need not have been this way, but it is this way. It is that there are very, very clear classifications. Actually, I'm gonna show one picture because I just love this picture. If I have it up here, I do have it up here. Just blah, 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 there's Pluto. We're gonna go to this picture because I love this picture. Here are the planets of the solar system, Mercury, Venus, Earth, Mars. You almost never see them at their real sizes because people love to make graphics where they're all more or less the same size. But here's the real sizes: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Here's Pluto. This, it doesn't really fit the pattern very well. Here's the asteroids. That's Ceres at its real size, top 10 biggest ones. And even just looking at this, and actually if I think on the next slide, I throw in, I don't throw in the Kuiper belt. I'm going to zip through this. There we go. Kuiper belt objects are right there. So now that's the planet I'm looking for. Haven't found it yet, so ignore that one for now. Here are the Kuiper belt objects that have been found. Pluto's right there, Eris. It is very easy to look at the solar system from the perspective of like an alien flying in for the very first time, and you would very quickly say, oh look, there are these 4 giant gassy things. Call them whatever you want. I don't care about the name, but you would classify them together. You would then say, oh, look, inside those 4 giant gassy things, there are 4 rocky things also on circular orbits. Cool, we'll classify them somewhere else. And then as you got closer, you would see these asteroids in between, and a bunch of them, not just in between, but other places, but mostly in between. You would put those in one other basket, and you would put all these things in another basket. Occasionally, you might see a comet. You can decide where to put those. And not all these objects are neatly classified between Kuiper belt and asteroid and comet. But it's pretty clear that these are distinct categories. And as a scientist, we use these classifications to start to ask the questions that are important, like, why does our solar system have an architecture like that? How did these things form? And if you get the categories wrong, if you put Pluto as a planet, or even Pluto and Eris as a planet, and you said, how do the planets form? You would have to answer, well, these 8 ones form this way, but these other 2 form the same way that the rest of these Kuiper belt. You just start to go into crazy ideas. So to me, the words, the concepts are most useful when they help to explain the categories that we really use as scientists to explain what's going on.